Hi, I'm Darren, and welcome to Level Up Double E Lab. Well, this is it, the 10th and final episode on my simple amateur radio receiver project, and I have a lot of material to cover today, so let's get to it. A couple of episodes ago, I promised to show my CW decoding methodology, so here it is. Let's start with looking again at the adjustable bandwidth crystal filter. At its narrowest setting, the data I measured shows its passband going from about 8998.6 kHz to about 8999.6 kHz. That's a 1 kHz width, which is usable for CW, but not really ideal. Better CW filters are a fifth of that or even narrower, but I do have that decent notch filter that will be useful for knocking down adjacent signals. For now, I'll put the IF signal right in the middle of the filter at 8999.1 kHz. I say for now because in the future I might add an IF shift function to move it a few hundred hertz off-center to provide some additional QRM attenuation. Here's the frequency plan diagram. In principle, it is simpler than lower sideband and upper sideband, primarily because there's no spectral inversion to deal with. I'm making the safe assumption that there's signal energy only at a single frequency, 7050 kHz in this example. I need to get that frequency through my crystal bandpass filter, so doing the math, again for high side injection, means I add 8999.1 and 7050 to get the VFO frequency that I need, and that's 16049.1 kHz. Now that I've got my IF signal at 8999.1 kHz, I need to mix it with a BFO signal to make it audible. And here comes a slick little trick. The difference between the BFO frequency and the IF frequency will determine the pitch of the sound that I hear. For example, if I want to hear a 600 Hz tone, then I need to mix the IF signal with either a high side injected 8999.7 kHz BFO signal or a low side injected 8998.5 kHz BFO signal. I chose low side injection because doing so causes the pitch of the CW signal to increase as the dial is tuned above the transmission frequency. Choosing high side injection would create the opposite effect. The CW signal pitch would decrease as the dial is tuned above the transmission frequency. It's just a matter of personal preference. One final comment on my CW strategy. I added a new menu feature in my software called STFREQ, which is short for Sidetone frequency. It allows me to adjust the pitch of the received CW signal by slightly changing the BFO frequency. So if I want to hear an 800 Hz tone instead of 600 Hz when I'm zero beat to the transmission, I change the BFO frequency from 8998.5 kHz to 8998.3 kHz. I've set limits in the software from 200 Hz to 1200 Hz just to keep it within a reasonable range. Okay, that just about does it for all the design, theory, calculations, spreadsheets, graphs, LT-SPICE simulations, all that material I put together in all of these episodes to show the depth of design work that I went into. With one exception, I do have some material that I put together on the EEPROM that's inside the Nano and how I used it to keep track of that ST frequency setting, along with several of the other parameters in between power on and power off cycles. However, I'll show that material at the end of this episode because right now I want to get this guy powered back up and demonstrate some of its basic functions and do a very common measurement technique to quantify its sensitivity. What I'd like to demonstrate now is how the software and the hardware recognize a new batch of bandpass filters. So I had off-screen changed the bandpass filters from the 30, the 12, and the 17 meter that were in the receiver the last time it was powered up, and now has the 40, the 20, and the 15 meter filters. So if you recall from a prior episode or two, I showed how I'm using the analog input of the Arduino to detect a simple resistor divider. Then each filter has its own unique voltage output. So in order to set the receiver, so to speak, for the new combination, what I do is go into the menu. And it's that simple and that fast. It read the 3 analog input values and it reset for the 3 filters, and it changed the top menu to show the 3 that are now loaded. And because the VFO settings can't still apply from the prior set, they're reset to the default values. In episode 5, I went into detail about the notch filter. Now let's hear it in action. What I'm going to demonstrate here is one of the most common scenarios where you'd use it. It's when you've got 2 or more CW signals that are close enough in frequency to get through your IF filter. Remember that my filter here is a kilohertz wide, which is pretty large for CW copy. By using the notch filter, you can selectively knock down in volume one of the signals to improve your ability to hear another signal. Listen now as I use the notch filter to knock down the strong CW signal and let the weaker ones in the background come through better. It's not perfect, of course, but in crowded conditions it does help quite a bit. In this demo is how to use the variable bandwidth crystal filter to reduce interfering single sideband signals. In this case, I'm trying to listen to this ham working the Michigan QSO party. There's another fellow transmitting up frequency. His signal sounds like a very high-pitched squeak. Listen now as I narrow the filter to knock down the squeak.
QRZ Michigan QSO party. Kilo 9, Chloe, Easter, 59 Wayne County. November 8th, that's why it's about Romeo. CQ, Michigan Field Day, CQ, Michigan Field Day, November 8th, that's why it's about Romeo. November 8th, that's why it's about Romeo.
And just like the notch filter, it's not perfect, but it does make a noticeable improvement. Here's a quick demo of 20 meters.
It was probably all changed and changed long gone, but yellow CF roadway, the evening road drivers all got the mileage.
And another quick demo of 15 meters. All I could pick up that day was the FT8 crowd. I'm going to perform a common receiver test. It's called the noise floor test, or sometimes the minimum discernible signal, or MDS test. And it's very common, like I say, to run this on a receiver. And basically, it's trying to quantify the weakest signal that you could say that this receiver could pick up. And by quantify, I'm actually going to take a stab at getting an actual number in dB. And ordinarily, there's, like a lot of these tests, a very well-specified procedure with very high-tech equipment. I am trying to follow the ARRL receiver noise floor test. It's actually a published document. It's paragraph 5.1 that outlines very well how to run this test. I don't have all the equipment, but I've put together what I think is a defensible procedure to at least show some comparison of how sensitive the receiver is, and certainly to be able to show how each of the bands, each of the 10 bands that I built this for, actually work compared to each other. So I have run this test to get the numbers off screen, and I had the equipment set up across my workbench. I've just stacked everything for the sake of the video so that it's easier to see, and just run a demo of how it works. So it starts with a signal generator, and I've got my big boy out, my HP 8657A. Now I do have a 20 dB inline attenuator before the cable goes up to the input of the receiver. That's mainly just to provide a good impedance match from the output of the signal generator. The input of the receiver may or may not be a good solid 50 ohms, and I know this 20 dB attenuator is, so I just have to factor that in when I do the actual calculations. No big deal. I have the speaker connected, and across the speaker I have the only thing I can really use to check for the difference in the voltage output to determine the minimum signal. I just put it in AC mode. Now, more professionally, you'd use an actual audio power meter and be able to measure it more precisely. But this will work fine for the purpose of what I'm trying to do here. Now, before I start to test, a couple things for the receiver. I want to make sure I have it on CW mode, which I do. I want to have the filter, in this case, turned all the way counterclockwise. That's the narrowest filter. That's the CW filter. I have the RF gain set to max. I have the notch filter disengaged. And with that, I'm ready to go. Okay, to actually run the test, in this case I'm on 40 meters, what I have is the signal generator set 20 kilohertz above the lower end of the band, and that is standard per ARRL. I didn't use that for all of the bands. In some cases, my bandpass filters have a center of the pass band shifted above the lower end of the band, so what I did was adjust that frequency to be right in the center of the pass band. In other words, so I can get the maximum sensitivity from the receiver. Now, when I turn on the receiver here and then turn on the signal generator, we can get a tone coming out. And what I want to do is adjust the frequency slightly until I get a peak here. Because really what I'm looking for is to make sure I have the receiver set to get the maximum amplitude for the IF filter, which is not perfectly symmetrical and has a little ripple in it. So we want to try to find where that peak is. So just by slightly altering the tune of the receiver. So right about there is pretty close. That'll work. Okay, the next thing I want to do is set the AF gain to max. Again, where there's no signal coming out of the signal generator. And then record that value. So that's about 31 millivolts. And because I'm looking for a 3 dB gain above that value, doing the math, that works out to 43.7 millivolts. So the last thing I do here is turn on the signal generator and dial in the amplitude until I hit about 43.7 millivolts. Getting closer. It does bounce around a bit. It's not a very steady reading, but I'd say that's pretty close. So that's minus 108 dBm. So if I plug that into my spreadsheet and subtract 20 dB from that, remember I have the attenuator here, that's telling me that my MDS here is minus 128 dBm. And that's actually not too bad. And as I said earlier, I did run this test on all 10 of the bands that this receiver supports, and I'll show on screen a table of the results. 160 meters was the best performer at minus 140 dBm. All the rest, with two exceptions, were at minus 125 dBm or lower, which that's pretty good. I mean, I'm satisfied with that result, certainly with the level of sophistication this little receiver has with a single IF super heterodyne and no other fancier filters. That's not too bad to be able to get that level of sensitivity. Now, the two that weren't so good were 15 meters and 12 meters, and I think I know the reason there. When I was doing the fine-tuning of the bandpass filters, I really was getting either too much passband loss or not really able to get those filters to peak right where I wanted to. So in both cases, the signals were kind of going through the skirts of the filters, which is never good. So a little more work to do there, but otherwise, pretty happy with the performance. The last software topic I want to talk about in this episode is how I use the EEPROM to keep track of data. It adds a lot of convenience to have the various BFO values, display brightness, sidetone frequency, and so on stored and recalled between power cycles. Looking at the hardware details, the Atmega 328 has 1K of EEPROM, which is more than enough to store that data, which I've grouped into this structure called EE settings. Breaking down this 62-byte structure, it uses 5 instances of another structure called VFO, which itself is 10 bytes. There are 5 instances of this structure because there are 2 VFOs, A and B, and 3 filter banks. I use the 3 filter bank instances to keep track of the VFO settings when you're switching back and forth between the 3 filter banks. The remaining data values are of interest to save, things like the display brightness, for example. I skipped over the first parameter called ID. That's a 4-byte unsigned long integer that I'm using as a trick to get more life out of the EEPROM. What I mean is, if you look at the specs for the Atmega 328, each cell of EEPROM is rated at 100,000 write cycles. If the receiver had a soft power button, there'd be no worries. I'd only be writing to the EEPROM as part of the power down sequence of the receiver, and it's hard to imagine ever reaching 100,000 power cycles. But I don't have a soft power button. Turning the receiver off will immediately cut the power, and there's no way for the Nano to detect that condition and write to the EEPROM before losing energy. So instead, what I'm doing here is just periodically saving those settings. Meaning inside the main loop function, I'm running an activity timer that monitors the 2 encoders. It's sort of like a watchdog. It keeps track of how many seconds have elapsed since either the frequency or menu encoders were moved or pushed. If enough time elapses without any manipulation of the encoders, then a write cycle is triggered and the timer stops. The timer remains stopped until an encoder is moved, then the timer is reset to 0 and a new countdown begins. Let's say I set the inactivity threshold to 10 seconds. That's a reasonable time interval to wait, but if I'm writing the data to the same cell addresses, it does raise a concern. Assuming worst case, if I tune the radio, then pause for just over 10 seconds, then tune again and wait another 10 seconds and repeat this over and over, I'll reach the specified cell limit after 1,000,000 seconds of radio usage. That equates to just under 278 hours. Assuming I use the receiver for 4 hours every day, I'd reach 278 hours in about 70 days. Setting aside any debate over whether I'd really use this little receiver that much, there is a simple software algorithm that I can use to extend that life by about 16 times. That algorithm simply expands the writing and reading process to use nearly all of the 1K of EEPROM and not just use the first 62 cells over and over again. What I did here was parse the 1024 bytes of EEPROM into sectors of 62 bytes each. That's 16 sectors or 992 total bytes. That's the max. There's not enough remaining memory to get a 17th sector. So all I need now is an algorithm at startup to read the correct sector and an algorithm to write the sectors sequentially when doing new data writes. That's where the ID parameter comes into play. It's basically just a counter. On startup, I read the ID from all 16 sectors and then pick the largest value. That particular sector will have the most recently saved data, so I load from it. While the program is running, every time a new write cycle is triggered, it increments the ID by 1 and then writes that ID value along with the parameter data to the appropriate sector. The quote-unquote appropriate sector is calculated as just the remainder of the ID divided by 16. Once it reaches the 16th sector, the next write cycle starts over at sector 1. So going back to my original life assumption of 70 days, I've now extended it by 16 times to over 3 years of usage at 4 hours a day, every day. That's high enough now that I should have no worries about worn-out EEPROM. We can debate whether that much life is really needed for this little receiver, but at a minimum, the principles I used here are commonly done with EEPROM and are extensible to other applications that may have a more serious need to maximize EEPROM life. So that is a wrap. That's the final episode on this 10-episode project that spanned about 5 months of me working on it part-time. And it sure was a lot of fun, especially getting into all the calculations and diagrams and simulations that I did. I really did learn a lot about how super heterodyne receivers work. And of course, like I said early on, this was my first Arduino project, and I wanted to do something a little grand, and I'm very happy with how it turned out. I have a lot of miscellaneous topics to cover here at the end, but before I get into that punch list, I want to extend one final thanks to Jim Forkin, amateur call sign WA3TFS. It was his original material that got me started on this, and he gave me a lot of good tips along the way as I added my own modifications. So thanks very much, Jim. Okay, and looking at my list off to the side, the first thing I want to talk about here is I didn't do the AGC circuit demonstration. It actually turned out to be really easy to set that. It only took me about 5 minutes to dial it in. If you do want to see more details about how to do that calibration, illustration, it's in Jim's article in QST Magazine in the August 2021 issue. If you were eagle-eyed, you would have picked up that my S meter is off. It's really over-reporting the signal strength, and I have to go back in and recalibrate it. It pretty much shows any signal over about an S5 as being an S9, so I have some adjustments to make there. Next item, I did not make that broadcast band high-pass filter that I mentioned in a prior episode. I did some more experimenting with the circuit, and what I found was that I traced down that the broadcast interference was it was intermittent. I could only hear it occasionally, and it did not look like it was coming in through the antenna, which could be another problem similar to what I had with the microphone preamp, where I'm picking up broadcast signals either on the headphone cable in this case, or maybe even the power lead. So more experimentation is needed to figure out what's happening there. I also want to talk about software one last time in the end of this episode. If you remember, I was pretty adamant about wanting to make efficient software and keep the size small. And since I did that video, I added more features, so that generally means the software is going to get bigger. It did a little bit. My final total, according to the Arduino IDE, is 25,078 bytes of the flash RAM consumed and 834 bytes of the RAM reserved. So ended up with a pretty decent amount of free RAM there. And I've been using the receiver. I haven't had any issues with it locking up, so I should be fine with that much RAM free. The final topic I want to cover here are changes that I might make in a version 2.0. It's always a fun exercise to think about things you might change or do differently if you ever did a future version. So here's what's on my mind. First and foremost is the crystal bandpass filter. Now, the components that I chose seem to be working generally okay, with maybe the exception of those varactor diodes. I didn't select those to match them. That could contribute to the funky shape, but layout is also important, as I've learned here with filters, and just kind of haphazardly putting the components wherever they kind of nest well together on the circuit board is not really a good idea. So if I do another version, I would definitely prototype the filter design and optimize that before I committed to the final design. Another item, I would definitely seriously consider making a transceiver next time. If you recall in my first episode, I brought that question up.
Why just build a receiver? Why not build a full-featured transceiver?
After building the receiver, I can certainly appreciate it would be a lot more useful to be able to have two-way communication than just one-way. So that's definitely something to consider. It adds a lot to the complexity, but certainly adds a lot to the features if you can transmit and receive out of the same unit. Another item is the audio stage. It's working very well, but it occurred to me that since I've got the audio already broken out, it would be so easy to just have that as a separate DSP module and add a lot more sophistication, maybe even better filters. All the things that go with modern DSP, you can get it's essentially on one integrated circuit. So that's very interesting. Maybe I would consider doing that in the future. Certainly the size of the case was a restriction, and I did get everything to fit nicely into this little Archer case, but there's no room for a speaker, and that's kind of a shortcoming. I'd really like to be able to listen to this with an integrated speaker and not have to have one on the outside or headphones. So that would necessitate a larger case for sure. And then the last item on my short list is the graphics. I think I'd really like to take a stab at silk screening next time. You can get fairly economical home silk screening kits now, and that would be a slicker way than just having this laminated piece on here. I think that would be a neat thing to try next time. And one final comment before I close. This is about the third week of April as I'm filming this, and just a few weeks away, the 20th through the 22nd of May, is Dayton Hamvention 2022. I'm planning on being there on Friday. I will be spending the majority of my time in the flea market looking for future projects on Level Up EE Labs. So if you do happen to run into me, please say hello and introduce yourself. If you've been watching this series since the beginning, thanks very much. If you've subscribed to my channel already, a double thanks for that. And as always, I hope you enjoy the material I'm putting together here. So until next time, bye for now.